Alright, welcome back to some, does this count as algebra or number theory? I actually have no idea. And I should be clear, the curly braces are the fractional part. What the heck? Yeah, unfortunately the braces are like completely oh god. Left, right. Left. Right. Okay, beautiful. Plug random stuff. We can like maybe kind of here's the thing, all right? For any particular x comma y you plug in, that left hand side is irrational or zero. I mean, we don't care about zero. But like if the left hand side is non-zero, it's irrational. Do I believe like the true answer is irrational? I mean, actually it's a strict inequality. So like the best will if I plug in like a lot of values of x and y, the best thing that will happen is that I have a bunch of square roots I need to approximate, and I can get like the decimal approximation for like what I think the answer will be. I agree C is the most one. That much I support. I will tell you now that C is like bigger than 0. Let's assume x bigger than y, alright? Actually, is it better to have x bigger than y or x less than y? I never know. I would believe 1/2. I would. I have a lot of... Let's do x less than y, alright. So the point of this x less than y thing, like, one is that we do have to actually use the condition that y is not equal to x, like, you know, because otherwise I think the answer... If you allow x equals y, the problem is stupid, because then the square roots are literally like x squared plus 2x plus 1, right? Is x plus 1 squared. So you can get the fractional parts arbitrarily high. And what makes this problem not stupid is the fact that we actually explicitly throw out the x not equal to y. And so then what happens is that square root, you know, this guy here is actually explicit. It's square root blah blah blah, and you know, that's the fractional part, because the integer part will be y. And I think the thing I usually do with this is write it like... This is a true identity, right? Sorry, 2x. This is a thing you can do with square roots to make it a little easier to see how big it is, because if you have the minus sign, it's very hard to tell. Here, it's okay, you know, this is what it is. And nominally, like, if you let x be like very close to... Actually, is that true? If you let like x equals y minus 1, the fractional part of square root y squared plus 2x is quite big, right? Yeah. So if x is slightly less than y, this number is... Wait a minute. What? Hang on. No. Oh, okay. For us, big means like close to 1. And is that true? Yeah. So if x is like really close to y, this number will be pretty close to 1. The kicker is that we think that square root x squared plus 2y in that case will be pretty small. And how hell if I know. How well can you do with real numbers? Oh, if it's real numbers, you can probably get... If it's real numbers, what you do is you let x and y be like off by a very small amount. Like you let x be like 10,000, and then you let y equals like 10,000 plus 0.001 or whatever, and you can get as close to 1 as you want. Yeah, that's the problem. Yeah. X less than 2y makes c too small. Yeah, 2x less than y. Yeah, I would believe x about y over 2. In fact, why don't we just check that? We can just check that, right? We will actually just say if we let y equals like 2n and x equals n, we should have so square root x squared plus 2y is equal to square root. Now let's just say for n bigger than like 1,000, 100,000, whatever. So x squared is like n squared plus 4n. So this is a pretty good fractional part because it's like just under n plus 2 all squared. Wait, actually, that is a really good fractional part. What the heck? Yeah, that's close to 1. And then the question is if I go the other way, y squared plus 2x. I feel like the thing is like you kind of think that at whatever the optimal situation is, the two fractional parts should be pretty close together. Like somehow it feels like if one of the fractional parts is like really close to 1 and the other is like, you know, half-ish. It feels like you wasted some potential or something. I don't know. How big is the fractional part of this thingy? This is like, it's like about half, right? Because we think this is around, no, actually it's actually less than that, I think. This is like a quarter. Because the thing is like root 4n squared plus n is like about 2n plus 1/2 all squared. No, sorry, 2n plus a quarter all squared. So this is actually really bad. This is like a quarter. So... Yeah. Yeah, so, yeah. X is phi. I think the problem with phi is that it's like... Like, if x is about phi y, well, okay. What you could do is you could try to plug x and y as consecutive Fibonacci numbers. That is a thing you can try. That'll actually probably do, like, pretty well. It'll do better than this, I think, because this is pretty bad. If I plug in just, like, consecutive Fibonacci numbers... Oh, that's so hard to think about, though. Oh god. The answer's gonna be irrational, isn't it? Do you get like 0.6s if you plug in? Do you actually get things close to the golden mean? I wouldn't be surprised. Yeah, okay, so we're gonna throw away the 2 and n. That really bugs me now because, oh god, how are you gonna show that this is best possible? Okay, I think I agree Fibonacci is, or any like, if you let x over y be about the golden ratio, or sorry, y over x because we have y large. Yeah, I agree that'll give you about that. That's probably as good as you're gonna get, because you got them at like, at least it's like a local like max or something. Like if you want to do better, you'll have to use something completely different. But I think my feeling is that the fractional part mostly depends on just the ratio x over y, so there's like not anything different you can do anyways. In fact, I want to make that precise. I feel like the fractional parts only depend on the ratio y over x in some sense. What do I mean by that? Well, oh god. I think the problem I'm having is like, if y is much larger than x, it's really hard to say anything about what this fractional part is. Like if y is much larger than x. Oh, but that won't happen, because the point is that if y... Okay, I see where this is going, I think. Oh god. Alright! What is there... What's the notation for 0.618? I know phi is 1.618. Is there one that's better for... like... Okay, we'll just use k like a... Oh no, that's awful. We're going to use k, alright. Okay, consider two cases. Okay, this is what we want. Because the point is, if assume x is greater than y. So if y and x are about the same size, by which I mean x is greater than ky, and versus if x is like not big enough, then y is y squared plus 2x yada yada is less than y plus k, right? This is just true. If x is too small, then so the fractional part will be less than k. And if we think x and y are about the same size, well, then we're happy, I hope. Maybe. We'll find out. I think the goal is that I want to be able to trap x. Like, because x and y are similar, I should be able to trap the size of x squared plus 2y. So on the one hand, it's less than x, and on the other hand, it's less than x plus something. What's the something I want? Fuck. Why was this an equality case? Because we thought that... Sorry, the point is this is bigger than x plus 1, right? And we claim that it's less than x plus k plus 1. So the left hand is true because like it's literally just more. Y is strictly bigger than x. That's where we use the fact that it's not equal to y. And then the right hand side should follow because I square it. And then you know, k squared plus 2k plus 1 x. And the point is, the whole point of k squared is that 1 plus k squared is like 4kx. That's just fine, right? I feel like I dropped a factor of 2 somewhere. Hang on. Yeah, fucking heck. Wait, no, sorry, I'm a stupid head. 2k plus, wait, what? Wait, guys, how do you square shit? I'm so bad at this. Oh my god, this is embarrassing. 0.6. Okay, cool. We're fine. Okay, yeah. So this is what we want, and then oh yeah, sorry, I dropped the k plus 1 square term because I don't care about it. I really don't want to write up the other direction because it's like shortlist 3 minus root 5 over 2. Oh god, that problem. Yeah, this should work. This is what it should be. Define clean. I mean, okay, the other thing is, like, you can, if you use Lucas numbers instead of Fibonacci numbers, it's probably slightly less annoying. Because you only care about the consecutive difference, right? And so it's like, you literally just substitute in alpha. Yeah, if you're going to use Binet's formula, use Lucas numbers so you don't have this stupid 1 over root 5 factor. Alright. Alright, let's just write this up and then I'll wing the bit about the construction on the fly. Did the previewer show up? It's here. Okay, so the answer is C equals... Oh, okay, we didn't need to use K because we could have just used the letter C. First, we prove this works. Okay, oh, I think that's confusing. Notice that... Then observe that whenever x less than ky, we have and then conversely, whenever ky, and assume x less than y without log. Okay, this is x plus 1, this is x plus k plus 1, which is what we want, so good. Thus, in each case, one of the fractional parts is less than k. Yeah, and the problem is that because these inequalities are strict, like I can't use a single xy. Conversely, for the construction, we just, the idea is that x over y should just be stitch pick y over k approx k. To that end, define alpha is k plus 1, beta is k, and consider the numbers x equals alpha to the n plus beta to the n. Is it plus or minus? I think it's minus. Where, you know, this has to work, so why did you just redefine k as c? I don't know, because c looks c. They use c in the problem statement. I don't want to stop. I don't know. Okay, like. You think I should just reuse C? I mean, everyone will know what you mean, but it's also just, yeah, I agree, though. Yeah, this is, well, it's going to be two fractions. So as I mentioned earlier when I was doing this simplification, yeah, we really only care about the ratio. Okay, we'll just see. I feel weird because, like, I don't know, it's capital C, but it's less than 1. I feel like you would want it, like, I don't know. Y over x, and this is like exactly equal to 2 over root c squared plus y over, it's like alpha, right? To the end, let No, I hate this. We're using alpha beta. We're using alpha beta. Okay, these are integers. Oh, is it minus beta? Are you serious? Oh, fuck. Alright, thanks for the tip. Whatever makes them integers, I don't care. Shit, I should use Fibonacci's. These are integers because they are consecutive Lucas numbers. And similarly, yeah, it's basically it must work because the error term drops to 0. Like the error term in the previous calculation just drops to 0 and it's alright. shit, I fucked up. This is 2y. Oh no. No. I should put this on a separate line, honestly. And then, Lord. 2y minus 2x minus 1, right, is what it works out to. And then here's like y minus x. This is so annoying. Like, it just works, right? Because the dominating terms. Alright. We know it works. You just have to write it out. And then take the limit. So x over 1 y minus x. Yeah, this just approaches 1 over alpha minus 1. Did I do that right? I feel like I didn't get the right number at the end. Yeah, so the Lucas is a little overkill. Like, all you need is x, y are A, big, and B, their ratio approaches alpha. And this is just, like, me annoying. 2 alpha plus 1... I feel like I didn't get the right constant at the end. Oh, because this plus 1 shouldn't be there. This one's just, like... Could even take, like... SML representations. Yeah, actually, honestly... I should just not do the Luca thing, right? Because it just looks dumb. Well, I'm gonna write it this way. Because I feel like the Consider any sequences of integers, positive integers. Okay, and then instead of alpha here, I just write C, 1 over C. It's just increasing for simplicity. Yeah, good enough. I wonder what happens if you, instead of 2, I don't know. Oh, I dropped all the I dropped all the subscripts if I'm doing it this way. Oh, crap. Come on. Analysis. It could be analysis. I feel like the main analysis part is that, like, if you understand the concept of a limit well, you have less agony writing the construction. Actually, well, if you don't understand limits well, the construction is going to be really, really hard to write up. Because it's just, like, you have to manually deal with all the random error terms that are cropping up. And you want to have enough machinery that you can just ignore the error terms. But I think the process of figuring out that the correct construction is to have x over y be 0.618 actually feels a lot like equality to me. Like, I was considering putting this in the equality unit up until I got to this part here, and I was just like, it's like there's an execution step that is technical, so it's like, But like this is equality 100%, I think. Z equality. I feel like it's too easy for Z equality, honestly. I feel like this is the kind of problem where, like, if you've like done stuff like this anymore, like, you know pretty much what you're going to do the whole time. I think it's like more instructive if you aren't used to this kind of argument. And if you're like at a level that you're doing Z equality, I think most of the people taking that unit won't learn much from an argument like this because they've probably done it a few times already. Like, I think, like, at first I was a little worried because I wasn't sure what the answer was, but like, I think as soon as I realized that 0.618 gives you about the same fractional part, after that I knew what I was doing the whole time. Like, there was no point where I was like, I'm worried that going down this route isn't going to finish. Because I got the equality case and I can see exactly why it's the equality case. So. Oh, they literally just wrote O of 1. God damn it. Yeah, that's fine. That does actually work because, yeah, that's smart. Oh, that's smart. Yeah, you can actually just, if it's big O of 1 inside, it's a little O of 1 outside. That's a fair point. Damn. Yeah, that's actually cleaner.